I guess maybe it's time to smoothly start our today's seminar. So, dear colleagues, it's my pleasure to introduce you Dr. Anton Frisk Kockum, who comes from Chalmers University of Technology in Sweden. So today he will present us a talk on giant atoms, a new frontier in quantum optics. So Anton, please, you're welcome.
Thank you very much, Maxime. So I will share my screen again and start the talk. And turn on the laser pointer. All right. So I'm happy to take questions at any point during the talk. Maxime will help me also to read out any questions that you put in the chat, I think. So yeah, please feel free to interrupt me for questions at any time. So today I'm going to talk about giant atoms, a new frontier in quantum optics, a new regime in quantum optics, illustrated here on this fancy first slide. And this illustration is an artist's impression of an experiment, which I will explain later in the talk. So you will understand everything that's going on this slide later. But so to give an outline for the talk, I will start with answering, I think, the question that's on everyone's mind right now: what is meant by a giant atom? So we'll talk about sizes of atoms and their development. Then I will talk first about the physics of a single giant atom, before moving on to physics of multiple giant atoms. First some theory, and then I will talk in particular about this experiment, which is illustrated on the first slide. And I will summarize and give some outlook for this field, where I think there is really a lot of interesting physics to explore. Okay, so let's look at atom sizes. So the topic here is really quantum optics. So we're talking about the interaction between light and matter. So here, for example, cavity with light with photonic modes, and some green atoms here that can interact with the light. And yeah, we're dealing with this interaction at the level of single photons, single atoms. This is a field that's been studied for many decades. So you could think it's been quite well explored, but it turns out there are some new regimes that are not explored that much, mostly because really experiments were not going on in these regimes, or couldn't reach these regimes. But thanks to some new technology in the past few decades, especially superconducting qubits, which can make artificial atoms, we can reach some new interesting regimes of quantum optics. So to speak about giant atoms and their size, let's first say what is a small atom. So usually in quantum optics, we think of atoms as small. And when we talk about sizes here, small or giant, we need something to compare with, right? And what we are comparing the atom size to is the wavelength of the light that the atom is interacting with. And usually in nature, this the size of the atom here in red is much smaller than the wavelength lambda here of the light it interacts with. This allows us to make the dipole approximation, where you assume the atom is point-like, and you can neglect any spatial variations in the electromagnetic field. So you just have to take into account what is the value of the field at this one single point where the atom is coupled to it, which makes life easy for theoreticians. And as I said, this is sort of the case in nature. If you think about natural atoms, radius of an angstrom or so, and natural optical light with wavelengths of a few hundred nanometers, you see that the atoms are much smaller. This is also the case if we look at so-called Rydberg atoms, which are highly excited atoms. The electron is in a highly excited orbit, so they have quite a large radius. It can be tens or even hundreds of nanometers. And in these experiments of Serge Haroche, who got the Nobel Prize in Physics in 2012, where they're looking at quantum optics with these atoms, they are having these atoms interact with microwaves, which have much longer wavelengths. So still here, the atoms are definitely small. Also, if we look at some more artificial atoms, for example, quantum dots, that are coupled to, for example, a photonic crystal waveguide here, we also have this situation, the atom is small. And for superconducting qubits, which I will explain in some more detail later how they work, here the electrical circuits that function as artificial atoms, they are larger. You have some capacitance here in yellow. So these circuits, they can sort of be micrometers, hundreds of micrometers large. But they are again interacting with microwaves, sort of like in the Haroche experiment, such that they are still small compared to the image. Now,
may I ask, maybe, sorry for interruption. So just for the last slide, since I'm from semiconductor physics originally, so it's one example I know. So there are Rydberg atoms, but also there are these Rydberg excitons, which got relatively famous maybe 5 years ago, where you have, say, cuprous oxide, and they have been able to observe excitonic states with main quantum number up to 25, but because it's exciton and not an atom, I think the size can be up to 10 microns. So it's, I've just realized, so is Rydberg exciton in that sense another giant atom?
So yeah, I actually just recently heard about these Rydberg excitons through my student, who is also present here. I'm not sure what wavelength of light they are interacting with.
So it's basically optics. So you have some yellow band, green band. So it's, but maybe it's unrelated. So there are some problems because it's semiconductor and as usual some inhomogeneous and everything.
I don't know. They might be breaking this dipole approximation. They might not be as simple giant atoms as the one I'm going to talk about. But I should check that out. Okay. So let me show you what the kind of giant atoms I'm talking about here. So I'm talking now about some atoms that can couple to the electromagnetic field at multiple points. Here, for example, 2 points that are wavelengths apart. So I think it's a little different from the example you talk about, because there it wouldn't be sort of discrete points at which you couple, but you would couple continuously over several wavelengths, which makes the problem more complicated, I guess. But it turns out you can make these atoms that couple just at sort of each point is small here, but you're coupling at multiple points that are far apart. And this gives some interesting interference effects, basically. The fact that you're coupling at multiple points, wavelengths apart. So the reason people hadn't really looked into this theoretically, I think, was there were no experiments even close to this regime until a few years ago. So what really got this work started was an experiment at Chalmers University of Technology, where I am now and where I was also a PhD student back then. So in the experimental group of Per Delsing, they were working on superconducting qubits. So superconducting qubits, they are basically, you can think of them as electrical circuits on LC oscillator. And to make them more like an atom, sort of with differently spaced energy levels, it can't just be an LC circuit because that's just a harmonic oscillator. It's too simple. So what one does is you add, instead of the linear inductor here, you have a Josephson junction or several Josephson junctions, and they act as a non-linear inductor, basically. So you get an anharmonic oscillator with different transition energies from 0 to 1 and from 1 to 2. Now, I mentioned these before as examples of small atoms. What made them giant in this experiment from Per Delsing was that we were not coupling them to microwaves of the electromagnetic field, but we managed to couple them, or they managed to couple them to sound or surface acoustic waves. So here's an artist illustration of this setup. So you have some substrate, and these surface acoustic waves are vibrations that are confined to the surface of the substrate. And now to couple them to electric field, what you do is you have this substrate be piezoelectric. So these vibrations in the substrate will come with charges being moved. And then what you can do is you can apply here oscillating voltage between these two electrodes in orange here across this interdigitated structure. So these fingers of the electrodes, they will alternately push and pull on the substrate. And this, if you have the spacing right between these fingers, so you're on resonance, so to speak, with a wavelength of surface acoustic waves, the vibrations you want to generate, you generate a wave that propagates out there. And then what you do is have the qubit, the superconducting qubit, be shaped similarly. So the capacitance here in the qubit is shaped in this interdigitated structure, such that when the vibrations on the substrate come here, they come with some charges moving, they will induce charge on this capacitance of the qubit, and in that way coupled to this circuit. So we could basically make phonons in the substrate coupled to the superconducting qubit.
So may I ask, just, I think I understood it, but is it correct that all the interaction mechanism, that the interaction between the surface acoustic wave and the qubit is just piezoelectric, so due to some potential induced in the qubit? So
yes. Yes.
The qubit is not deformed because naively I could think that
that's correct. No, the
wave somehow changes the shape of the qubit.
It's just through the electric potential. The deformation of the substrate is, it's I don't know if it's picometers or something. It's extremely small.
So, and just to understand better, so I know a little bit that you could couple your qubit, for instance, to the transmission line, so to electromagnetic wave, and instead you use surface acoustic wave. This is just because the wavelength is larger of the surface acoustic wave.
Yes. So I will show that in the next. So here in this first illustration I had of superconducting qubits, this part in dark blue in the middle, that's the transmission line. And so, and the outer parts here are the ground planes around the transmission line. So then you just have a capacitive coupling between this qubit in the yellow here and the transmission line. But so yeah, the new thing here was when we coupled to the surface acoustic waves, we were still working at microwave frequencies, a few gigahertz. But since we are now coupling to these sound waves rather than light, speed of sound is many orders of magnitude slower than speed of light, so the wavelength is accordingly much longer. So in this case, here's a picture of the sample. So basically this structure shown here in the illustration is this blue structure in the middle. And then you have separation between fingers here was about, quarter of a wavelength. And you have many fingers across the structure, so you have like tens of wavelengths across this structure. The wavelength is around a micrometer. And then the extent of the qubit is 15 micrometers or so. So you are coupling at many points. So each of these fingers is like you're coupling at one point here to the field. And these points are quarter of a wavelength apart in this case. So this was really, when they were doing this experiment, they came to ask us theoreticians, well, how do you calculate properties of this? This is how we started investigating giant atoms. And then when we started thinking about it, so I have this first theory paper in PRA in 2014. I'll say a bit more about the physics shortly. We realized there were more setups where you could realize such giant atoms. You could go back to the sort of transmission line that's usually used with superconducting qubits, and just sort of you have it capacitively coupled here to the capacitance of the qubit, and then you could sort of meander it away on the chip such that it's wavelength distance or so, and you come back and couple sort of again to the same superconducting island of the qubit, and go away and come back. This you could fit on a chip, couple a few times like this. And this is what's been used in some recent experiments. I should update this reference. It's published just the other month. But I will talk about this paper in Nature that I had from last year. They're using this technique to implement giant atoms. Then there has also been suggestions that you could use cold atoms in optical lattices. So what you have here is lattices that are defined by counter-propagating lasers. And then you have atoms trapped in these potentials that are formed. And you can have two internal states in these atoms. That sort of one part represents trapped emitters of the atom part, and one moving photon. And sort of each of these states feel a different lattice. And if you rapidly change the lasers, you can sort of move the photon lattice around such that you effectively couple to several points in this photonic lattice. So this is some sort of effective giant atom that you could construct. And this is then in 2D, a 2D lattice, rather than the one-dimensional transmission line here, for example, in the superconducting qubit examples. And there are some interesting effects there in 2D. Yes?
So this whole structure acts as one atom, or it's one atom in every lattice in some sense?
I think you could have multiple atoms in this setup. They're just showing one here.
Okay, okay.
So it's like, I think the atom is sort of fixed, sitting at the fixed point in the red. I'm not sure how they are moving things. I think it's blue lattice, and then you're moving the red lattice around, or you're moving one of these lattices around such that the atom effectively couples to several points. Okay, so now that we know that these systems exist in nature, we want to see what's the new physics here for giant atoms. So yeah, let me just first say here that these works that I'm going to present, I mean, it's the result of many collaborations with both experimental and theory groups, Chalmers, Oxford, Waterloo, too many people to mention. Okay, so if we just look at the single giant atom, so the first study we did. So we know single small atom, it's coupling to at a single point to this transmission line. Now we're looking at a system with we have a small atom, we have an atom and it couples at multiple points, x1, x2, x3, to this one-dimensional transmission line, where you have a continuum of photonic modes or phononic modes, depending on your experiment. And the take-home message here shortly is just having these multiple coupling points means you have interference effects. Say, for example, when the atom, if the atom is excited and it decays into the modes on the transmission line, it can emit from this point, or from this point, or this point. And depending on the distance here, if it's wavelength distances, we can have either constructive or destructive interference between these emissions. And that will effectively give a high or low relaxation rate of the atom. So one thing that's new that you need to think about going from a small atom to a giant atom like this is that you have a new time scale in the problem. And that time scale is the time it takes to travel between these coupling points in the transmission. So for the purposes of this talk, I will only consider cases where this travel time is small, negligible compared to the relaxation time of the atom.
So is it like a Markovian approximation?
It's like a Markovian approximation. Yes, exactly.
Thank you.
We have a few papers also where we have looked at the non-Markovian case, where you really have hundreds of wavelengths or really long distances that this travel time matters. And there is an experiment also done with this with these surface acoustic waves at Chalmers, where you sort of see revivals of the atom. You emit from these points very far apart, and then what's emitted at one point later is absorbed again at another point and re-excites the atom. But for now, let's work in the Markovian limit. So we can write down Hamiltonian for the interaction between the two-level atom in this case and all the modes J in the waveguide coupled at all the points xk. And we see that we get this phase factor here due to the positions of the coupling points, and then v is the velocity in the transmission line. And if you sort of do the normal derivation for tracing out the modes of the transmission line to get the master equation for just the atom to describe its relaxation, you get the relaxation rate that depends on sort of the density of states in the transmission line, and this factor, which depends on the coupling strength in each point, and then these phase factors.
So Anton, may I ask you a question regarding these coupling constants? So you assume that they depend on the coupling point, but they do not depend on the type of the mode. So well, could you explain this a bit more?
Okay, I think I used a somewhat simplified version here of the Hamiltonian. I think in the paper we also assume it depends on the mode. Mm-hmm. Yeah, it's a sort of simplified presentation.
Right, thanks.
So yes, and what you see is this is like a discrete Fourier transform of the coupling point coordinates basically, and also the coupling strength. This means that you can, in principle, by choosing the coupling point coordinates and the coupling strength, you can design any frequency dependence of the relaxation rate. So the relaxation rate will depend on the transition frequency of the atom. And you can design how it depends by choosing the coupling points. So you can mimic, for example, some structured environment for the atom. You could design some atomic transitions to, at some frequencies, we couple very strongly, and other transition at other frequencies we couple very weakly to the environment. So let me show here first the simplest case. If you have equal coupling strength and you have equal spacing between connection points, so everything is as symmetric as it can be. What you get then is this frequency dependence. So in solid lines, I show the relaxation rate gamma. For blue, it's with 3 coupling points, and red is with 10 coupling points. And then here as a function of the distance between the coupling points. So the 1 here means that the distance is 1 wavelength. So that's when you have constructive interference, and the distance is 1 wavelength between each. That's when you have the maximum relaxation rate. And then you see it's basically a sinc function that you get here for the variation of the relaxation rate. And then in the dashed lines, I'm showing the lamp shift. So the renormalization of the atom frequency due to the interaction with the transmission line, which also acquires a frequency dependence. So this was the most symmetric case. Then I'm showing here some examples. If you play around with these coefficients, the coupling strengths and the positions, you can basically have any frequency dependence here for the relaxation rate. I just made a few different examples where you have the red, some wide minimum for the relaxation rate, and blue, some wide maximum. Black, you have 2 different maxima, and so on. You can design anything you like, and we will use that in the experiment I will talk about later. But this is basically a take-home message. That for a single atom, you can design frequency-dependent relaxation rates. Okay, then let's now talk about what happens if you have multiple giant atoms. And we will see one phenomenon in particular, which we call decoherence-free interaction, which arises there. So after we had looked at the single giant atom, I gradually started investigating what happens if you have more than one giant atom. Is there something new here that small atoms can't do? And a few years later, this was finally published in a PRL here. What I did there was compare a few different setups. So in A here, we have 2 small atoms coupled to the transmission line. B shows the same thing, but the transmission line terminated. Error. And then you have giant atoms coupled for these sort of 3 different topologies, 3 different geometries, 3 different orders for these coupling points that turns out we need to separate. So to compare all these, you can derive master equation, so tracing out the transmission line again, just getting an effective equation for the dynamics of the 2 atoms. And for all of these setups, the master equation is on the same form. You have the bare atoms with the renormalized frequencies, and they have some exchange interaction mediated by the transmission line. Then they have individual relaxation into the transmission line, and also collective relaxation term. So what differs between these different setups is the coefficients in front of these terms. So to understand here what's going on, let's just remind ourselves what can we do with two small atoms first. So here with two small atoms, I mean, you can certainly, even though the atoms themselves are small compared to wavelength, the distance between the two atoms can be on the order of wavelengths. So you can have wavelength difference here, or corresponding a phase that you acquire traveling from one to the next can be 2 pi or more. And you have some different interesting cases here. If you put the atoms one wavelength apart, so the phase is 2 pi, you don't have any exchange interaction in this Hamiltonian anymore. Turns out that's proportional to sine of phi. You have a maximal collective decay, which is proportional to cosine of phi. And in this case, you have some interesting superposition states here. You have what's called a dark state, this antisymmetric superposition, where it turns out that if you were to have emission on these atoms from this dark state, so emission from the second atom will be cancelled by the emission from the first atom due to this minus sign here and the distance being 2 pi. So due to destructive interference, this state is dark. That is, it doesn't emit any radiation. The symmetric superposition state, on the other hand, you get constructive interference. So you get emission at an enhanced rate. This is why it's called bright. So the lack of emission from the dark state is called subradiance, and the increased radiation from the bright state is known as superradiance. Then, yeah, if you change the distance between atoms, you have other points here. So, for example, pi/2, where you have high exchange interaction without any collective decay. But you always have the individual decay of the atoms. You cannot decouple them sort of from the transmission line. There's only this one particular state that can be protected from relaxing into the transmission line. Now, the giant atoms, it turns out, are somewhat different here. So let's plot now this exchange interaction, the individual decay, and the collective decay as a function of the distance between neighboring coupling points with phase difference phi. So there's a lot of lines here, but I'll walk you through it. So the black lines is the small atoms. And then we see here in dashed black line, we always have this individual decay. And for some values of phi, we have also an exchange interaction. For some, we don't. Now, we know that from the single giant atom, we know that, okay, we can make the phase difference here pi, then we will not have the individual decay. We have this frequency dependent relaxation, right? So if we see, for example, here, these separate giant atoms, I call them, in C here, that's the blue lines. We see here that the individual decay goes to 0 when phi is equal to pi, so half a wavelength between the coupling points. And at this point, also the collective decay in dotted line and the exchange interaction, everything goes to 0. Maybe not so interesting. But the special one is the what we call a braided setup here in D, where they are intertwined, so the coupling points. It's one for the first atom, and then one for the second atom, and one for the first atom. So here, this is the green lines. You see, if you look at the dashed lines, the individual decay, it goes to 0 here at pi/2, and also the collective decay goes. So all the decay goes to 0. But in the solid line, we see here that the exchange interaction is non-zero.
So do I understand correctly? So because it seems like a very important point. Naively, I would think that if a small atom does not decay into the waveguide, atoms don't talk to each other. So if any of them does not emit decay in the waveguide, it means that it does not emit photons. It means that atoms cannot be coupled just because they do not decay into the waveguide.
Exactly.
But here it does not. It is not like this. So individual atom is decoupled from the waveguide, but still there is some interaction.
Exactly. So this is the new thing here. This is the difference between small and giant atoms. You can have this sort of protected interaction. That is, they can interact via the waveguide without decaying into the waveguide. And it's sort of because we have more connection points here, the interference effects in this setup work out to suppress the decay, but still allow the interaction. And it's something you can't do with small atoms. So this is the main result of multiple giant atoms.
But then,
and
Anton,
in case, sorry, Maxim.
Yeah, so the question is whether we connect, what happens if we connect several atoms in this way? Do we still suppress the decay of the whole system?
That's the next slide.
Right, thanks.
So, yeah, well, this was sort of, I show now the case for two atoms and two coupling points. And we show then in this PRL that once you understand how it works with two atoms and two coupling points, you can take that intuition and generalize it to many atoms. All interactions are still pairwise, so you just need to look at two atoms at a time. So here is one example of a chain of atoms connected to a waveguide. So if you look at them in pairs, so the first and second atom here, they are in this braided setup with alternating coupling point from one, coupling point from the other, coupling point from the first again. So they can have this protected interaction. Now, the first and the third atom, they are not braided, they are separate. So they are in this case. So there, you cannot have this protected interaction. So when you set the interference such that the individual decay is 0, then they will not interact. And so on. So you can look at each pair of atoms here, see, are they braided or are they separate? And then you know if they have protected interaction or not. So in this case, this effectively is like a 1D chain, the nearest neighbor couplings, nearest neighbor protected couplings without any decay. And you can calculate the decay is proportional to the phi, the phase difference between these two inner points. That's what sets the coupling strength for that protected interaction. And I show here an example sort of how you can make this setup quite easily in the transmission line waveguide with superconducting qubits. You meander it like this, have each qubit coupled at 2 points to this transmission line, you get effectively this setup. Then you can have, we show some other examples in the paper, I don't have it here, some more complicated setups, so you can have more all-to-all coupling if all qubits sort of are braided pairwise, you can have all-to-all coupling protected. But yeah, all interactions are pairwise, and you can just use the intuition we gained here from this slide to understand which atoms will interact or not.
So I just have totally, my intuition does not work here at all. So for a pair of atoms, as you said, there are protected interactions for nearest neighbors. For second nearest neighbors, there are no protected interaction.
In this
so
setup, yes.
yeah. So if you calculate the collective modes for a whole array, including all the coupling after you diagonalize the problem, will there be some some protected excitations with infinite lifetime in the whole structure?
That's not something I've really really looked into. That could be interesting to check. Here, you're thinking about sort of dark state.
Yeah, because my intuition is completely broken for this system. I would, on one hand, it's periodic, so there should be some Bloch waves and everything, but here it's something very, very interesting. But I guess it's
So I think the point I'm trying to make with this protected interaction is that it's not a dark state. Like this dark state, you had a very specific superposition of states, right? Here doesn't matter what the states of the atoms are. The whole Hilbert space is protected from decay into the waveguide. And then, so you tune all the individual giant atoms to have destructive interference in the decay. So, but it turns out they can still interact through the transmission line. Now you could have, of course, setups where you allow some decay, and you have some particular dark states. Then we have looked a little at this. We have a paper actually, a preprint coming out in a few weeks, hopefully, where we look at chiral quantum optics, so the possibility that you have different relaxation rates going to the left and to the right, sort of what the physics. We say a few things about dark states there, but yeah, that could probably be explored further. Okay. Let me then just finish by showing this experiment.
May I also ask you before you start? You show that your atom have 2 points for connection, but could be it more points?
Yes.
And what we need to do to get more points?
Yeah, you need to connect some more points to the waveguide. We treat this in the paper, this PRL. For the many giant atoms. I also give the formula for arbitrary number of connection points. But it basically reduces it. Whether or not you have this protected interaction depends on sort of which of these 3 types of setup you have. Also, when you have more connection points, if any of the connection points are such that it's sort of braided like this, you can have this protected interaction.
Then it means that with 2 atoms, you can make any setup which you need with some kind of collective effects. Like it would be the same if you have n atoms or you have 2 atoms with many connections. You will get similar effects.
N atoms with 2 points versus 2 atoms
versus
with 2 points.
Yes.
I'm not sure. Yeah,
every connection acts like a separate atom in some sense.
But it's still still just two atoms. I don't think you can think of separate connections as separate atoms.
Maybe in non-Markovian approximation, because in Markovian you somehow at the end of the day you trace out all your connections and then you just have two atoms left. But if you go beyond Markovian, who knows?
Yeah, that's more complicated, of course.
Also, it seems like a very difficult mathematical problem. Say if you have two atoms, I guess you have shown all possible ways to connect two atoms, and all of each atom has two legs. But if you have, say, three atoms with two legs, or with three atoms with three legs, it seems like really already a mathematical problem. How to calculate all different ways to break them. Very interesting.
So for the non-Markovian case, what's published are just studies for a single giant atom. So first we had one paper on one single giant atom with two connection points far apart, and then last year we had another paper with a single giant atom with three or more connection points. Already there, you got some new interesting physics when you had three or more connection points instead of two, actually. You got some oscillating bound states where you could trap, you had some state, a bound state, where excitation was trapped in the giant atom, but it was sort of oscillating between being in the atom and in the transmission line between the connection points. But it just never leaked out outside the connection point.
It's just amazing, because I think one of the main topics of research in this laboratory, completely unrelated, but maybe not that unrelated, are so-called bound states in continuum, when you have some cavity, some resonator of specific shape, and you engineer the radiative decay by changing the shape of the resonator. So just some dielectric resonator. And on one hand, it's something very different platform. On the other hand, maybe some ideas.
Yeah, definitely. This paper was also bound states in the continuum, basically.
It's like quantum braided by bound state in continuum in some sense. Yeah, thank you.
Yeah, so I'm a co-author of this paper, so if you look on archive or Google my name, you will find it. Okay, I see I've sort of used the 45 minutes, but I hope I have time to show the experiment, if that's fine.
Yeah, no problem.
Okay, so let me show this experiment then, where a group of William Oliver at MIT, who are really good at experiments with superconducting qubits, they really confirmed sort of these results I had for 1 and 2 qubits. And they did it in this setup with transmission line coupled to the qubits. This is sort of what's shown in the illustration in the first slide. It's from this chip. So what they have here are 2 qubits in yellow. So basically, that's a superconducting island, and then it's capacitively coupled to ground plane. And in this small part, there is this nonlinear inductance, this Josephson junction, or it's 2 Josephson junctions in a so-called squid array, actually. So you can, by changing magnetic flux through this loop formed by the 2 Josephson junctions, you can change the effective inductance, and thus you change the resonance frequency of the qubit. So you can tune the resonance frequency of the qubit, which means that in a way, you're tuning the effective distance between coupling points, because the transition frequency sets the wavelength of the radiation that you're interested in. So here, in this case, here's a schematic of the chip. So you have this first qubit, it couples at one point to the transmission line, it meanders, couples to the other qubit, goes back, couples to the first qubit again, couples to the second qubit. So it is this braided setup that I talked about that has this decoherence free interaction. And then they can read out each qubit individually. Okay, so what they first did was to look at a single qubit and check that you have this frequency-dependent relaxation rate. So they tuned one of the qubits far away in frequency, and they just measured one of the other here. And they tuned then this qubit frequency over about 1 gigahertz here, around the point that corresponds to the distance being half a wavelength between its two coupling points here. So the minimum is where you have half a wavelength. And they saw, here's the relaxation rate. They saw it fitting very nicely with theory and achieving this minimum. It's not exactly 0, but there was a decrease by an order of magnitude in the relaxation rate from like, an increase by an order of magnitude from like 3 microsecond relaxation time here to 30 microsecond relaxation time here. This 30 microsecond relaxation time is really close to state of the art for superconducting qubits that are not coupled to transmission line but used in quantum computers, and we try to keep them as isolated as possible. So this remaining decay is not to the transmission line but to some other sort of environment, some parasitic coupling that it's hard to get rid of.
So the record is what is about 100 microseconds, right?
Yeah, I would say
so,
in the good quantum computers now from IBM, for example, they have 100 or a couple hundred microseconds.
Okay.
But then there's no waveguide there. Right? Okay. Then, so when they confirmed this, then they started looking at if they could see this protected interaction. So now they used both qubits, and they tuned them on resonance with each other, and then they tuned them in sync, sort of over a few hundred megahertz. And they measured from a readout, they could see from detuning the qubits slightly from each other, they could see an avoided level crossing. And the gap here indicates this effective interaction between the qubits via the transmission line. So this G, they plot it here in the red dots as a function of tuning the qubits, and it's fitting well in theory. It's not supposed to change much over these frequencies. But what's notable here is, if you remember from the previous slide, at this point, around 4.6 gigahertz, that's where we had the minimum for the decay into the transmission line. So despite being at this point where you have no decay into the transmission line, basically, you still have a clear high non-zero coupling via the transmission. And then we stepped up the experiment a bit to try to use this protected interaction for something interesting. And to do this, we made the setup slightly more complicated. We made 3 coupling points per atom instead of 2. And we played around a bit with the distances and the coupling strength at each point, making the one in the middle a bit higher coupling. And the reason for this was that we could now have the following frequency dependence for the relaxation rate. So in blue here is the measured frequency, measured relaxation rates as a function of frequency. Now we have these 2 minima instead of this single minima we had before. We have 2 minima that are a few hundred megahertz apart. And at both of these minima, we have a non-zero interaction strength in red here. So that means we can now turn this protected interaction on and off while keeping the qubit sort of protected all the time by, if we want to turn them off, turn the interaction on, we put both qubits at the same protected frequency. If we want to turn the interaction off but keep the qubits protected, we put one at each of these frequencies. So they are off resonance with each other. So that's what we did then. We start with one qubit at each of these frequencies. We excite one of the qubits, and then we tune the other qubit to that frequency. So we turn on the interaction, the protected interaction, and then we tune it back and we read out. And we can see as a function of interaction time here how the populations in the two qubits oscillate back and forth. And if we stop here at this halfway point where we've transferred half of the excitation into qubits, we have done what's called a square root of I swap 2 qubit gates. We prepared this maximal entangled state. We could do that with 94% fidelity. So yeah, what this means is that we can do these 2 qubit gates protected from decay between these atoms that are quite far apart. They are interacting via the waveguide. Since we can control the atoms individually, you can do single qubit gates on them as well. Together with this 2 qubit gate, we have a universal gate set. And this means that we can, in principle, construct any quantum state that we want, run any quantum algorithm. So this could be interesting then, for example, to prepare some complicated superposition state, maybe with more qubits in this protected way, and then you could turn them, tune the qubits to a frequency such that they would interact with the waveguide and release this entangled state, for example. This is something we want to explore further. Okay, so let me summarize. So I've talked about giant atoms, and what I meant by this here was atoms that couple to a waveguide or some environment light at multiple points, and the distance between these coupling points is on the order of wavelengths. So when you have these multiple coupling points in these larger distances, you get interference effects. For a single atom, that meant we could design the relaxation rate as a function of transition frequency. For 2 giant atoms, it turned out we could do something that you can't do with small atoms. We were able to completely decouple the entire Hilbert space. So not just a single dark state, but all states of these atoms from the waveguide. But even though due to the interference they were decoupled from the waveguide, they were still able to interact via the waveguide. And I showed you how these effects now have been demonstrated in the experiment with superconducting qubits. And we're looking into applications of this. So I mentioned this, we had this universal gate set. We can create some interesting states and release them to the waveguide, or if we can use this for quantum simulation, where we can do gates on the qubits and then turn on and off the coupling to the waveguide. We can hopefully do some simulation, which includes also an environment. And then, more generally, looking ahead, I would say people have just started exploring these giant atoms. Before this experiment, 6 years ago from Helsing, no one had really thought about looking into this because such systems didn't exist in nature. So this is a quite new regime in quantum optics, and we've just started exploring it. But I mean, quantum optics is vast. There are so many phenomena there that I want to revisit, and I think others could revisit too, to see if giant atoms can make a difference. So we have started on some of these things I mentioned here. Like chiral quantum optics I mentioned, we'll have a paper out soon. But yeah, there's still a lot more to explore, maybe some low-hanging fruit, I think. And if you want to know more sort of what's been done in this field, I have a review. It's published in a book. It's my easiest to find on the archive, I guess. So, summarizing the first few years of research on this topic. So with that, I thank you for your attention. I'm happy to take more questions.
Thank you so much, Anton. Very interesting talk. So now the talk is open for questions. Colleagues, if you have any, please raise your hands. So while people are thinking, maybe I will start from the first question. You mentioned that it is possible to design different couplings in different connection points. So I wonder whether it is sufficient to make different coupling strength to ensure some chiral coupling, or you need some extra ingredients. Could you comment on that?
No, I think you need some extra ingredients. When I say, for example, here we have different coupling strengths in different points. Mm-hmm. What it in practice meant was sort of here we have a smaller capacitance, and here you see we have a larger segment on the transmission line that gives a larger capacitance, larger coupling. But the coupling is sort of symmetric. So in each point, there's equal probability of emitting to the left and to the right. There's no chirality here. So you need something more to the system. It's maybe not so easy to engineer in superconducting circuits, maybe in other systems where you have atoms coupling preferentially to one or the other direction.
I think you still need to break reciprocity somehow. Yeah. There was a work on chiral optics with superconducting qubits, but I think they also had some additional ingredient. I just forgot.
Yeah. I think you could think about inserting sort of circulators at points in this waveguide to enforce certain propagation direction. But yeah, the setups become a bit more complicated.
Yeah, clear. So breaking spatial inversion symmetry is not sufficient. Okay, so some other questions?
Maybe I have a very general and naive question. So if you just want to have two qubits that are coupled, but without any decoherence, you could in principle do the same without any waveguide, just by having some capacitive coupling, or what is called just some nearest neighbor interaction without any waveguide and transmission line. So here, what is the novel opportunity that is added by in your setup?
One thing you can notice here is that, okay, maybe let's look at this picture instead. These two qubits are quite far apart on the chip. So you have an opportunity here to couple qubits that are more spread out across the chip, communicate over longer distances. And then there is also this, exactly, you can turn this interaction to the waveguide on and off by changing the frequency. So perhaps you can, as I mentioned, you can create some interesting state and then emit it to the waveguide. And that's hard to do. Yeah, if you just have two qubits without an environment, sure, you can make a coupler between them. But yeah, here you have this tunable coupling to an environment. You can turn on and off, and you have also interaction over longer distances. And as I alluded to when Alexandra and others were asking before. I mean, we have more setups than just this nearest neighbor. You can have braided, I don't have a picture right here, but you can have more complicated braiding such that you have not just nearest neighbor coupling.
Maybe, sorry for too many questions, just that this setup is so interesting.
Yeah, no, I'm happy to answer.
So I'm just a little bit confused. How does input-output theory work in this setup, or in maybe in experimental way? If I suppose that you have some protected state, protected from decay in the transmission line, either for one atom or for two atoms, so you don't have any decay. How then do you measure it in experiment if it's protected from any decay? How do you probe it?
Yeah. As you say, in this PRL, actually, I give in the supplementary some equations for input-output theory for this generalized case with many atoms and many coupling points. In the Markovan approximation, it works as input-output theory for small atoms also. So as you say, yeah, if you've tuned the interference such that the atoms are decoupled from decaying into the transmission line, they will not talk to any input. Yes, that's correct. What they did here in this experiment, for example, to measure the decay of the atom, was that they had individual readout resonators here in red. So a resonator, a cavity is coupled to the qubit and dispersively coupled, and so detuned in frequency, such that if the qubit state changes, you have a slight change of the cavity frequency. And then they probe the cavity here with a readout line and detect this change in cavity frequency that corresponds to a change in the qubit state. So that's how they measured these oscillations, for example. It was not through the waveguide at all, but through individual readout of the qubits through these resonators.
So another question related to the experimental part. So as you showed, these qubits are placed at the distance equal to 1 wavelength. So I wonder whether it is possible to put two qubits at much larger distances, let's say 5 lambda or 10 lambda. So there might be some limitations.
Yes, I think for sort of this setup, I think here you're starting to see that it's getting crowded on the chip with these three coupling points. So I think they can get 10 wavelengths on this chip, but 100 is difficult.
Yeah, but I mean, from the point of view of losses, 10 lambda is still okay.
Yeah.
No defects in the waveguide.
No, there are no. You can think of the waveguides here as lossless.
Okay, that's interesting.
Yeah. Then, as I mentioned, there is an experiment from Per Delsin's group with these surface acoustic waves. It's in Nature Physics 2019, where they looked at a single giant atom with 2 connection points very far apart. And there they had several hundred wavelengths apart. So they can do, with surface acoustic waves, you can do really long time delays, really long distances. With these superconducting circuits, unless you can make larger chips and so on, but it's harder to get out of the Markovian regime.
Thanks. So I do not see any other questions from the audience. So I suggest to smoothly finalize the seminar and thank you once again, Anton, for a very nice talk.
Thank you for having me. It was a pleasure.
Yeah, it was a pleasure for us also.